I want to welcome everyone to this session. I'm Suzanne Brenner, the current president of SIAM. It's really a great honor to introduce this year's SIAM lecturer, Qiang Du. Qiang is the Fu Foundation Professor of Applied Mathematics in the Department of Applied Physics and Applied Mathematics at Columbia University. He's also affiliated with Columbia's Data Science Institute. He currently serves as the co-chair of the Center for Computing Systems for Data-Driven Science. He has numerous awards and honors, including the Feng Kung Prize in Scientific Computing and the U.S. Association of Computational Mechanics Thomas Hughes Medal. He was an ICM speaker. He's a fellow of SIAM, the AMS, and AAAS. He also has a very impressive service record for the profession, most recently serving as co-editor-in-chief of the new AMS journal, Communications of the AMS, and he's also editor-in-chief of the SIAM Journal on Applied Mathematics, as well as being a member of numerous other editorial boards. His list of accomplishments and accolades is much longer, but we're here for his talk, which is titled Analysis and Applications of Non-Local Models. So I'll pass it to Qiang. Go ahead, Qiang.
All right, thank you very much, Sue, for the very nice introduction. And thank SIAM and JM organizers for inviting me, giving me this opportunity to talk about our recent work. I'm going to speak about analysis applications of non-local models. So let's begin the discussion. We'll start by talking about the term local and non-local. Local essentially represents some confinement to a position in space and instance in time. Otherwise, we think about this as being non-local. But mathematically, we can give a more formal definition, starting with a linear operator. A linear operator is called local if it does not increase the support of the function it operates on. Otherwise, it's going to be non-local. So clearly, polynomials of derivatives are local operators. But it's a curious fact that, in fact, essentially, all local operators are polynomials of derivatives. This is a theorem of Peter's some time ago. In other words, local models are essentially partial differential equations that we're all familiar with. Right? Now, at the same time, we understand that linear operators in most of the function spaces we're interested in can be represented as in this kernel representation form. For local operators, the forms of the kernels are very specialized, right? Otherwise, you can have more general kernel, then you'll end up with non-local operators. We work with non-local operators often, with or without realizing that. I give you a few popular examples here. Okay. And historically, there are also a lot of discussions about non-local interactions in physics and other application areas. This is ubiquitous in nature. But you may wonder why you haven't noticed a lot of non-local representations in the literature so much. Well, you're not alone. This is because often, if you make assumption that the quantity of interest are smooth in space and have slow variation, then you can do the so-called Landau expansion, or maybe simply Taylor expansions, and you can represent or approximate those non-local interactions by the local counterparts. Right? So that's why you end up seeing PDE most of the time. But in recent decades, I would say, there have been a lot of interest on non-local models, described by non-local model operators directly, ranges from PDE's analysis to many other areas, subjects of mathematics. For example, fractional PDEs. So here I give you an example of a fractional Laplacian operator. So this kind of object have been studied quite a bit in recent decades, connected to other problems in geometry and also versional problems. Related to this, there's also studies of non-local operators for anonymous diffusions, non-local diffusions, connecting that to stochastic processes. In image analysis, this has non-local operators are used a lot. For example, there are notions of non-local gradient I've given you here, and also non-local divergence, as well as non-local Laplacian. There are other applications of non-local models as well, studies. like non-local continuity equations, non-local conservation laws, and also non-local operators are used for optimal transport. Of course, there have been quite a bit of literature studying the integral equations that you see more often, like Fredholm equations or Volterra integral equations, as well as functional equations like equations with delay, equations with memory, and also the integral formulations of PDEs, boundary element methods, and so on. Okay. In the subject area of data analysis or lake analysis, you can connect notions of graph Laplacians with non-local operators. There's notions of diffusion maps and so forth related to non-local operators, as well as a lot of studies in metric geometry. The list can go on, but this just shows that, in fact, there has been a growing interest on non-local models in recent years. I want to draw your attention to a new focus that myself and my collaborators are interested in, which is on non-local operators of a finite range of non-local interactions, and also those can be operated on vector fields. So here I give you two examples of operators. The first one we call them as a non-local gradient operator. The other one is a non-local divergence operator. They have a special form in that their kernels in their integral representation, the kernels essentially is parameterized by parameter delta, which measures the range of their support. So in other words, those operators have only accounts for interactions on a limited range characterized by this parameter delta. Right? And the kernel function omega, for simplicity, can be assumed to be radially symmetric. It's a probability density function, satisfy a normalization condition. In addition, we're going to assume that as this delta, this range of non-local interaction, as this delta parameter goes to 0, this kernel function is going to get localized. It's going to approach a Dirac delta measure. So this will make a good connection between those non-local operators and their local counterpart. Indeed, we can ask in what sense those operators look like a gradient or divergence. You can make them to be the formal duality pair, so they're dual to each other. And also, if you operate on linear functions or linear vector fields, they actually reproduce the local counterparts, so they're exactly the gradient and divergence. So then for smooth functions, if you do Taylor expansion, then you can easily see that as delta goes to 0. So when they get localized, indeed the delta goes to 0 local limit of the non-local gradient and non-local divergence will also go to their local counterparts. Okay, so that motivates us to call them as non-local gradient and non-local divergence. If you find those integral forms more complicated to look at, here I give you a simpler form, which is the one-dimensional version for scalar quantities. Then really you just end up with a non-local derivative. And this looks like a weighted average of a divided difference. So naturally that resembles a space derivative. You can have the symmetric version. You can also have a non-symmetric version. Those non-local operators, when you take the kernel function to be of special form, like fractional powers, and when you set the delta, the range of non-local interactions to infinity, then in fact, they can reproduce the fractional operators, such as fractional divergence or fractional gradient. So this can connect with studies on fraction operators. Besides this pair of examples I've shown you, there are other ones. So there are non-local two-point gradient divergence, or you can call them as edge gradient divergence if you connect that with graphs. And this is very much similar to the non-local gradient, non-local divergence used in the image analysis. And you can compose them together to form a non-local Laplacian operator. Right? So in what sense this is a non-local Laplacian? It's an integral operator, but you can see that again, if you take delta goes to infinity, so the fractional limit, and for this very specialized fractional kernel, indeed, that limit goes to the fractional Laplacian. But on the other hand, if you wanted to localize, so if you actually take the limit when delta goes to 0, then the operator, the non-local operator will approach to a local limit, will be the standard Laplacian. Right. And with this non-local operator, then you can also consider, for example, the associated boundary value problems. A very natural setting will be, so for instance, because we have an operator L delta, which has a finite range of interaction. If you want to consider this like a non-local Poisson equation on a boundary domain omega, to have the equation L delta U delta equal to be well posed. When the points gets close to the boundary, the range of interactions has a neighborhood on the range of delta. You will see that to specify the equation, you'll need to know the values of U on the delta layer outside the domain omega. You have to impose some kind of constraints or conditions. So this is what we call as non-local constraints. For example, you can provide a tertiary type non-local boundary conditions, and together with the integral equation, and you can form a well-posed non-local boundary value problem. Okay, and now surprisingly, thinking about the connection, the fractional limit and the local limit, you can set delta goes to infinity to connect this non-local problem imposed on a domain with a finite layer to a limit where you have an equation inside omega, but you have data provided in the exterior. That's the fractional limit. And you can also set delta goes to 0 to get a local boundary value problems, the typical PDE you end up with the data specified only on the boundary. Right? So in a way, this non-local problem or non-local operator with a finite range can be served as a bridge to connect the two different limits. Now, you can also have variations of the pair of operators G and G star. You can take this operator D star, which is really a projected divided difference. You project that along this unit vector direction, and you can also define these two operators. Again, they also form a divided pair, and all those operators together, we call them as the basic building blocks or element of this non-local vector calculus. And you may wonder why we want to study those non-local quantities operates on vector fields. I'll show you some examples of application, or maybe better to say the motivation. And one of the motivation that motivated our study, me in particular, is this model of non-local paradynamics pioneered by Stuart Schilling and the Sandia National Lab for modeling elastic materials and fractures, propagation of cracks and so forth. So basically, paradynamics rewrites the classical Newton's law. Instead of taking spatial derivatives, you replace them by some integral form, which represents some kind of non-local interactions. Okay. This model of paradynamics has been quite successful in modeling various physical processes like fractures, and you get this very complicated fracture pattern that's very difficult to do with standard PDE theories. And we have also used that to model the growth of crack paths and so on. Okay. Now, although this looks like a successful story for some practical cases, and you will see that if you define non-local operators, then you can actually put this set of equations in a much more rigorous foundation. I show you this one example. Here I showed an integral representation of what's called a bound force. So basically, you think about particles within a range of delta, there are bonds connecting them, and they look very much like a hook spring, and then you collect all the spring forces together, integrate them over the interaction neighborhood to get a total force acting on the particle. So that formulation is in this complicated integral form, and it has its right physical meanings, but it's complicated. But if you use the non-local operators we defined before, you actually end up with a very elegant formulation. So if you want to write a force balance equation in this terminology, they will look very much symbolically like the PDE formulation you're used to, except the operators themselves are not necessarily local derivatives, but they're written in a non-local form. So non-local vector calculus, in a way, they can help you to reformulate this more complicated non-local integral model, but they also illustrate much better the mathematical structures of underlying physics, and they can further stimulate more mathematical analysis as well as development of computational algorithms. I will show you another motivation for coming from mechanics. This case is actually from fluid mechanics. There's a very popular numerical methods for solving fluid equations called smooth particle hydrodynamics. So you're not using any finite difference or finite element approximations, but rather using discrete particle simulations. In this SPH setup, this was again pioneered many decades ago with references I listed here on the slides. In the SPH approach, it basically involves a two-step process. You do not do the particle discretization of the PD alone. Instead, you first are going to smooth the so-called differential operators as a non-local integral operators. So basically, we're replacing your local derivative by some kind of non-local derivative. And here, you have a finite range of interaction, and that's typically referred as a smoothing length. So there's the smooth particle hydrodynamics. And once you get an integral form, then you can apply some kind of quadrature rule to evaluate this integral and the particle positions to get a more discrete form. And then you can solve the discrete equations to implement your numerical computation. Now, you have to be careful what type of smoothing steps you do. If you just replace a set of PDEs as a set of non-local integral equations, I mean, you can do that mathematically, but it does not always give you a good set of equations to work with. And in particular, some form of the non-local equations may end up causing stability issues that can become very much problematic when you further discretize in your numerical computation. So our message is that by studying this non-local vector calculus and non-local operators, you can form a better set of non-local accounting models, for example, a non-local Stokes equation, and they can enjoy much better mathematical properties, and they will lead to more robust and stable discretizations, right? So that's really the motivation and application of this non-local vector calculus and the non-local operators. Now, I won't have time to go into details of the specifics, but here I make a comparison of the basic elements of the classical local vector calculus and the non-local vector calculus. It symbolically looks like we're just mimicking what we know for PDEs for local theory, and then try to translate them into a non-local setting. But that's really not our goal. Our goal is to through this further development, is to offer new insight and perhaps a better understanding, not only on the non-local models, but even providing some new characterizations of PD models, if those PD models are available or valid for the physical processes or under consideration. Okay. So I'll show you some examples of this in my lecture today. So non-local model has strong motivations. It certainly provides a lot of research opportunities, but as well as challenges. And there are a lot of important questions to ask. Perhaps the most important one is to say, what kind of non-local interactions should we use for the mathematical form for different application problems, right? This is really a very important question, but we don't have a lot of answer to. There are many attempts and a lot of approaches, but largely there are many unresolved issues. I should mention that people have tried approaches ranging from phenomenological approaches to coarse screening or data-driven, all kinds of reduced order modeling. And we come to recognize really non-local interactions are like a generic outcome of this model reduction process. If you want to account for the unresolved details in a fine scale model, then you will very likely end up with certain forms of non-local interactions. And there are many examples like that, as I listed here. Okay. So we're really trying to obtain or construct non-local models or non-local interactions so that we can better tackle issues like heterogeneities in the physical process and other kind of complexities. And for example, the possible appearance of singular solutions or less regular solutions. And for those solutions, the differential equations themselves do not make sense point-wise. You have to interpret them in a weak sense. But for integral equations, they can make sense and a point-wise sense. Right? So, and there are other considerations for non-local interactions. we wanted to use them to capture the essential physics and maybe to help us improve our ability to make predictions and to get better outcomes. I show you one example that in a lot of heterogeneous environment, the diffusion process can be quite complicated, and there has been a lot of experimental studies and observations showing that there may be crossovers of different diffusion regimes. You could have a process that's showing on those pictures from those references, shows you that you could have a transition from initial sub-diffusion regime to a long-term, more normal diffusion regime, right? So we've used a non-local in-time diffusion equation to model this process, and it captured very well this transition from a sub-diffusion to a normal diffusion. In essence, what we showed is that for this non-local in-time model with a finite range of memory, then initially the finite memory actually is very important for the whole historical development. So therefore, you have a very important memory effect, and you're in a sub-diffusion regime. But over time, when you have a very long history, if you only have a finite amount of memory, then the memory effect is significantly less, and you're very much behaving like a more normal diffusion regime. And so that's a intuitive explanation, but this can also be rigorously analyzed mathematically. Now, I'll give you one last example. We're living in a world that we're seeing more and more connections from far away, right? And for example, we've been talking about connected vehicles or self-driving cars. So the cars can connect, can communicate through GPS, through cell phones, and so forth. And so you may be in a situation, you're in a car, but you may be thinking about driving, not necessarily just based on the environment of the cars next to you, but cars or traffic far ahead of you or away from you, right? So, well, we can model them more effectively, by accounting for this non-local range of interactions. We have done some work on this non-local LWR model for traffic flows, based on also some other works done by many other groups. But essentially, this is the message for the day. If you can design your driving speed by incorporate the density of the traffic, not only at the current position, but also the positions, for example, far away from you, ahead of you, in a suitable range with a suitable average to design your car traffic velocity, then you can have much better traffic situation. We can show rigorously that the solutions of this non-local traffic flow model can converge exponentially to a stable uniform flow, and this will be a much more desirable traffic pattern. And this kind of result, is not true for the local model, but with this modification of the non-local speed, then you can get better patterns from the model predictions, right? Okay, so talking about the motivations for the non-local interactions and how we end up with different models, of course, we need to develop mathematical theory and also computational tools to resolve those, to understand and resolve those non-local models, right? In terms of mathematics, certainly we should try to utilize tools already developed, over many decades for PD theories. There's so much work done in that areas. And certainly you can try to transform your non-local models into local model, right? And then you can better utilize the existing PD tools, and that has been done quite a bit, right? But there are also a need for, as I said earlier, like the non-local vector calculus effort to systematically develop new theories designed for non-local models. Particularly, there has been some work to develop mathematical theories for non-local models involving this finite range of interactions, right? And also for vector fields, so that you end up with system equations rather than just a scalar equation with scalar quantities. So study this kind of problems will offer a much richer set of mathematical structures than their scalar counterpart, right? And at the same time, with this finite range of interaction and its different limits, local and fractional limits, you can also draw natural connections to the study of PDEs, the study of fractional equations. And by looking at the discretization, you can also connect that with studies of graph operators and operators on networks and so forth. Right. There has been quite a number of results obtained in recent years, ranging from studies of non-local operators to non-local functional spaces, and so on. But let me maybe offer a couple of specific examples, right? So I'll begin with this very well-known example of superlative spaces, the so-called classical trace theorem. This is very useful to study, for example, a boundary value problem defined on a domain omega. You may have a function belongs to this well-known W1P superlative space. And if you want to define a boundary value problems with distributed data, then you know that its trace on the boundary belongs to this fractional superlative space, right? So that's very well established, very well understood, and it's important for studying local boundary value problems. But now we're in a situation where we're interested in studying non-local operators with a finite range and maybe non-local constraint value problems. So we're in a different scenario, right? We have a domain omega, but we're imposing possibly boundary data on a layer surrounding this this domain omega. Okay, so it's in this scenario, and you wonder if there could be an analog of this trace theorem, just like the classical case. You have a norm for the solutions over the whole domain, and then you have a functional space or norm for its trace defined on this delta layer, and whether you have this similar tracing inequality. And of course, you would like to say this has to be a suitable generalization of the local one, in the sense that if you do consider the delta goes to zero limit in a local limit, you would hope that your non-local trace space and non-local trace norm will indeed recover the local one, and so are your function space and function norms defined on the bigger domain, right? So the answer is indeed possible. We proved the theorems like this. So I'll show you that we were doing this for a special set of non-local spaces and non-local norms. So essentially, the non-local interactions we're considering, or this kernel involves a fractional type of interactions related to the distance between the interacting positions, but it's truncated within the range of delta. So it's not going to be a fractional norm, but rather it's going to be only involving fractional interactions when the points are within a distance of delta. Okay, so there's a truncation effect. Okay. Now, there will be a analog of the non-local trace space. You can define that accordingly. And indeed, for this set of non-local function spaces and non-local trace spaces, we can have this non-local tracing inequality. And you can also show that if you have a function defined on a layer, which has a finite trace norm, then you can also have a continuous extension into the whole domain that goes into the bigger space with this norm in the bigger space bounded by the trace norm on the layer. Okay. So this will allow you to give a categorization to say what kind of boundary data you can have when you wanted to study a non-local boundary value problems corresponding to this kind of non-local operators, right? All right, but there is another side of the story to this. While I mentioned that for this non-local problem, it's very natural to consider natural constraints. For instance, the trace on a layer surrounding the domain. Okay? But for practical considerations, it's also interesting. It's also an interesting question to ask if you can actually impose local boundary conditions, because people have been working with PDs all the time, and they're used to the notion of local boundary condition. So they have software packages to solve them, and they also always ask you what kind of local boundary condition you have. And now you say I want to use non-local boundary conditions, and then you may not be able to use those packages so easily. Well, can we impose local boundary condition or not? Well, not all the time. So there's one other reason we can explain is that in a setting, for example, for this exponent beta, if this beta is relatively small, like less than the space dimension, then essentially all your non-local spaces are just the classical LP spaces. And so therefore, we don't expect them to have well-defined traces on a low-dimensional manifold. And so we can't really use local boundary conditions in those cases, right? But however, there is a strategy because we recognize at the same time that although those spaces actually are like the LP spaces for a finite and bounded delta, in the limit when delta goes to 0, they do have a local limit that has the proper trace, right? That's the local, that's the consistent result that one can expect. So therefore, a possible strategy to try to impose local boundary condition is the following, is to say that we're going to try to maintain non-local interactions in the domain omega, but as we approach the boundary, we'll try to localize so that we only consider localized interactions, and therefore, as the non-local range of interaction goes to 0 when the points approaches the boundary, and then maybe we do pick up regularity, and then we can have well-defined local traces and therefore local boundary condition. So this idea of using a delta, this non-local range of parameter, non-local range of interaction, make it out to be heterogeneous in space or variable in space is a very important strategy to help us study local boundary conditions for non-local problems. Okay. And I will use this example to illustrate, and this connects to another work we did a few years ago. So this is a special case of what we did the previous slides, but now I'm just setting this case where beta equals to 0. This is like the simplest setting where you can see that this non-local interaction is actually independent of the distance between x and y, but as long as x and y are within the delta neighborhood, I will have this non-local, I'll have contributions in this non-local norms. Okay, so in the setting where delta is strictly positive, basically the function space you define here is just the standard LP space. And this is a pictorial depiction. We're considering a constant horizon throughout the space. Okay. But now we're going to make a change. We're going to place this delta to be a function that depends on the position. It could be constant in the interior, but as x goes to the boundary, we're going to require that this delta x is proportional to the distance of the boundary, and therefore, when it actually hits the boundary, delta will completely vanish and get everything localized. And with this change, you can actually get a new trace theorem to say that the trace space for the classical surjective space is precisely also the trace space of this non-local space with this heterogeneous localization effect. Okay, so that's because when we're getting close to the boundary, we are picking up regularity, and we can get a well-defined trace. Although away from the boundary, anywhere away from the boundary, we can recognize that essentially in a subset which is completely contained in the domain omega, in fact, any function which are only LP integrable, they will stay in our function space. Okay? So our function space is actually a much bigger space. They're not as regular as the W1P space. Basically, you need to have integrable derivatives. Here we don't. We can have functions interior which are completely just integrable themselves, and yet near the boundary, they're much better behaved and they have well-defined trace. Okay. So in this setting, this non-local analog of the classical trace theorem it is not only a non-local analog, but it's actually a sharp proportion of the local case. It covers local case as a special case. And the proof of this result also involves more delicate analysis. And this is really a very natural type of trace theorem, because why do you need regularity for functions far away in the interior? You don't. In order to have a well-defined trace on the boundary, you essentially only require regularity and a boundary, and that's essentially what this non-local trace theorem is telling you. All right. Now, having this heterogeneous localization is nice mathematically, but it also poses further challenges, for example, to numerical computation. Because now you're in a situation, you have non-local interactions with a range of interaction that varies in space. Sometimes it can be large, sometimes it can be small or going to zero, right? We may have to develop numerical algorithms to make sure that in some sense they're insensitive or they are robust with respect to the change of the parameter delta. If you have a numerical discretization of non-local models that enjoys this kind of property, we call this type of schemes asymptotically compatible. This was developed again some years ago. So I will illustrate with this diagram. And imagine that we have a non-local continuum model. This is parameterized by a parameter delta. And we can discretize that with a discretization parameter h, which could be mesh size or particle spacing. As we refine our numerical resolution, or as h goes to 0, we expect we have a good numerical method that will have this numerical solution converge to the solutions of the continuum non-local models. Okay, so this is the good news. But maybe this non-local model also has a local counterpart for some cases, for cases you want to do benchmarking, for example. And for those PDEs, certainly we have numerical methods and numerical solutions to approximate the solutions of the PDEs. So in the case, if there is a well-established connection between this non-local continuum model and the local PDE, right? If there's a consistency on the continuum level, then what asymptotically compatible scheme is really trying to do is to make sure that you have the same consistency and to the discrete level. So that no matter you get a diagram, this is going to be what's called a commutative diagram. No matter which path you take, you're going to end up with a consistent and correct result. Okay, it's very important for me to emphasize that if you have a numerical scheme that's not asymptotically compatible, then you're at a risk of producing perhaps convergent results. So they will get close to some result, but the result itself may be incorrect. So this is actually even worse than you have a numerical method that's unstable or divergent because you just get garbage. This case, you might seems to be getting something that looks reasonable, but physically incorrect. And this is going to be, very risky when you want to solve problems that's, very complicated and involving singularities, right? So asymptotically compatible discretizations are important for this kind of model involving parameters and involving different ranges of parameters. We first established this for variational problems, and then this has been generalized to many other settings and involving various type of numerical discretizations. And this asymptotically compatible schemes, the development of this, together with heterogeneous localization, also provides an approach to study more effective numerical methods for non-local problems in a different context. Okay. I should mention, really, non-local models are in need of effective, adaptive, and scalable algorithm, just like their PD counterpart, right? But one strategy comes in mind is that you can think about doing localizations. It's like in a multi-scale modeling context, you can try to apply some kind of domain decomposition. So I have a domain of interest, but maybe there's only a portion of the spatial domain where we expect that non-local effect is important. I wanted to use non-local models, and then in the rest of the domain, maybe I can just use their local limit. Okay. So this fits into the description of we should think non-locally, because non-local effect allow us to capture or return more physics and get the right physics, get the physics correct. But practically speaking, we'll try to take advantage of the local model and to simplify our computation, reduce our computational effort. There are, of course, many questions regarding what kind of coupling strategies, how to decide which part should be non-local, which part is local, what kind of efficient solver, and so forth. But as I mentioned, by doing this heterogeneous localization, right, and we can actually couple a non-local model in a seamless fashion with a local model by simply shrinking the horizon, and we can have a well-defined interface condition for both the local and non-local model. And then with the asymptotically compatible schemes, you can have one set of numerical methods which in the non-local region is going to approach to the solutions of the non-local model, yet in the local region, it's going to correctly identify the solutions of the local model. So that combination of those approaches can allow you possibly find a much more effective scheme to solve more complicated non-local models. Okay. So I think my time is running up. I will just maybe conclude my lecture today by saying that we see that non-local models provides you a more generic set of modeling approaches, connecting with the local, fractional, and also discrete models. They perhaps can be very effective to treat phenomena involving anomalies and singularities. I discussed just briefly some recent progress on both the application analysis, but certainly this area is only at a nascent stage and a lot of work to be done in the future. I should acknowledge that really some of the works I mentioned, the result of collaborations with many collaborators and colleagues, and also the list including many of my former students and postdocs. Without them, the work won't be possible. So I really acknowledge their support, and some of them will be speaking and JMM in other sessions. So in fact, let me, well, I have a list of references. I'll have my slides available on the internet in case anyone is interested. But to conclude, I just want to advertise that there are several sessions and JMM devoted to non-local models. Their times are there. And also we have created a online one non-local world community to facilitate the communication and exchange of ideas for people interested in doing non-local modeling, analysis, and computation. So it's unfortunate that we cannot have this conference in person. We have to remain locally in a sense, but I hope that we'll stay connected non-locally. So with that, I'll end my lecture. Thank you very much.
Thank you very much, Qiang, for a very interesting presentation. Does anyone have any questions? Please put them in the Q&A box if there's any questions from the audience. And while we're waiting, let me ask a question about the numerical schemes. Qiang, can you comment on the conditioning of the non-local problems?
So thank you. So your question is about conditioning. For example, if you have a linear non-local problems with this finite range of parameter, what would be the conditioning of the stiffness matrix, for example?
Right, correct.
This is an excellent question. Actually, the condition number relies on two parameters, both the mesh parameter H and also this model parameter, this range of non-local interactions delta, right? So in one extreme, if you have a kernel that's actually reasonably regular or maybe smooth, like a Gaussian kernel, then in that case, the non-local operator itself is really a bounded operator. And then the condition number will be exclusively only dependent on delta. It's like scale like 1 over delta squared. Okay. But on the other hand, if you're non-local operator, you're taking a fractional kernel, and the fractional power is going to limit that your operator is almost looks like a differential operator of second order. Then in that case, your condition number is more like order 1 over h squared. So anything in between, right? You can imagine, you can just interpolate, you probably get a condition number delta to some power, 1 over delta to some power, and times 1 over h to some power, right? So in other words, in short, the condition number depend both on the modeling parameter and also on the discretization parameter.
Okay, thank you.